So in our additional notes, first of all, I can show you a fancy word. Here is the branch of mathematics, combinatorics, that studies counting. And so there's just, combinatorics is just a fancy word for counting. And this first part of our unit is dealing with permutations, which is counting things where the order matters. So we've already learned some of this stuff, so we'll be able to go through this fairly quickly. The fundamental counting principle. This was the first strategy that we learned. This is where we make a space for each decision that we need to make. If you're buying this car, you have three decisions. You choose which color, then you choose which transmission, then you choose which interior. And when we use the spaces strategy, we like to, underneath the spaces, write something very short to describe what it is we're counting. And that would be short enough. By C, T, and I can see that you're counting colors. There's three choices. Transmissions, two choices. Interiors, two choices. So there's 12 choices in total. And the fundamental counting principle allows us to count things quickly when you have a certain number of decisions to make and a certain number of choices for each of those decisions. Now we've done questions with numbers, so if I have the numbers 1 through 7 and I wanted to make a 3-digit number, 3 decisions to make, if I wasn't allowed to repeat a number, once I used up the 7 it was gone, or if I used up the 5 it was gone, well I would have 7 choices for my first number, because it could be any of the 7. But if I've used up a number, how many choices do I have left for the second one? Then I only have 6 left, and then I've used up 2 numbers, so now I have only 5 choices left. Whereas if I were allowed to repeat a number, use 7 3 times, or 5 3 times, then there would be 7 choices all the way through. So we have to be reading the question carefully to find out, is repetition allowed? Is it not allowed? Your exam and your quizzes, it'll be really clear. Sometimes in the homework, it'll say using these digits. And when they give you a list, they say once you've used one, it's an actual one that's gone. So sometimes you might need some clarification with the homework questions on this. But now we're going to get into a part that we haven't done a lot of in our notes so far. How many 3-digit numbers are even and without repetition? I think you had a question in your homework earlier saying how many numbers are less than 60 and even, but you were allowed to repeat. In this one, you're not allowed to repeat. And this can cause a problem because if we would, and don't write this down, I'll do it in red. This is not the right answer. But if you would go through this, how we've done things up till now, we say, oh, we have 3 choices. How many choices do I have for my first number? And for this example, let's say we're doing the same thing. We're using only the numbers 1 through 7. So then how many choices would I have for my first number? 7. I could pick anything. Then how many choices do I have for my second number? 6, because I've used up 1. But then how many choices do I have for this last number? Because it's even. And some of you are going to say 3. Right? Because there's 3 even numbers. This is probably what you would do. But then I would say to you, I'd say, what happens if you accidentally chose the 2? Not accidentally, but you're saying in your first choice, you could pick any of the 7. What happens if you chose the 2? Then there's not 3 numbers that can go here. Then there would only be 2 numbers that could go here. But you don't know if you chose the 2 or not. And so it becomes a problem if there's a restriction and there's no repetition. We don't know if this is a 3, because it could be a 3 if you didn't choose an even number first. But it could be a 2 if you chose one even number. And there's also the possibility that you chose both even numbers, and it should be a 1. And so we have a problem, because we don't know what number to put in this last spot. So the way that we solve this question, where there's a restriction, is we say, well, instead of doing that even number last, why don't I do the even number first? And say, I have three choices. I'm going to put a 2, a 4, or a 6 in for that even number. And then I'm going to go to the other ones that don't matter. But now, how many choices do you have for your first number? You've used up one of the even numbers. You don't know if you've used the 2 or the 4 or the 6. But you've used up one of them. How many numbers are left then for your first digit? There would be 6 choices left. And now you've used up 2 numbers. So there's 5 choices left. So you need to do this first. If you have a restriction, you need to deal with your restriction first. And so we end up with 90 different even numbers. So I want you to try this one. Again, using the numbers 1 to 7. How many are odd? And I'm pretty sure I can guess, because I just taught it to you, what technique you're going to use, which is great. But after you've used that technique, I want you to look back at example 2 and example 3 and see if you can see another way that you could figure out how many they're odd using the results that we got in example 2 and example 3. So most of you probably did this first, right? You said, there's my restriction, has to be odd. There would be 4 choices of odd numbers, 1, 3, 5, or 7. Those are lucky numbers. And after you used up 1, there'd be 6 choices left. After you used up 2, there'd be 5 choices left for 120. So my question is, how could we use example 2 and example 3 to figure out this same thing? Well, in example 2, or example 3, we figured out there was 90 even ones. In example 2, we figured out all of them. Without repetition, all of them was 210. So how does this help us find out how many odd ones there would be? Now, if you just subtract them, if you take all of them and take out all the even ones, what are you going to be left with? All the odd ones. And sure enough, it gives us the same answer. Now, in this situation, I think the spaces and dealing with the restriction first is the easiest. But we're going to run into some questions where this strategy down below will actually be much quicker and more helpful. And so much so that I gave this strategy a name. I call this the not strategy. And I call it the not strategy because you're counting what you're not supposed to. To find out all the odd ones, we count the even ones. We count the opposite. And if you take all the possibilities and subtract the bad ones, you will get your answer that you're looking for. Does that make sense? And so sometimes we'll do questions that'll say, how many ways can you put at least one boy on this committee? And it's going to be hard to count because it could be one boy, or it could be 2 boys, or it could be 3 boys. But then later if you think, well, what's the opposite of at least one boy? No boys. And that'll probably be much easier to count. And so this not strategy is going to come into play. How many 3-digit numbers can be created using the numbers 0 through 9 without repetition? This unit is also about semantics, about wording. So first of all, what's a 3-digit number? Is this a 3-digit number? Yes or no? What number is that? 92. 92 is a 3-digit number. Is it? No. 092 could be a 3-digit code, but 092, if that's 92, 92 is not a 3-digit number. So first of all, we have to understand, what does this mean? 3-digit number, right? 001 is the number 1. It's not a 3-digit number, but it could be a 3-digit code, right? It could be important if that's like your agent number 007 or something like that. But this is not a 3-digit number. So then when we go to do our 3-digit numbers, do we have any restrictions? Yes. We have a restriction on our first digit. It's anything but 0. And so we have to deal with that restriction first. Well, it happens to be our first number, so that's not so bad. But how many choices would we have? There'd be 9 choices. And if you're not allowed to repeat, how many choices do you have for the second one? You'd have 9 again. Why? Well, there's 10 digits. The first one can't be 0, so that's why there's 9 choices for the first one. Now you've used up a number, but now you can add 0 back in. So of the 10 digits, 0 gets added back in, but one number's gone. Now there's 9 left. And then there'd be 8 left after that, giving us 648 different 3-digit numbers that don't repeat. The other way you could do this is you could start at 100 and write all 3-digit numbers out and then just cross out the ones that repeat. If that's quicker for you, perfect. But I think this is a little bit faster. So what happens in this unit is we start developing strategies. And so far, if we were to list the strategies we've learned so far, we have done, I'm going to call it the fundamental counting principle, but it's probably easier to remember as a strategy as spaces. This was our fundamental counting principle. And as a subset of that, we've learned that you have to deal with a restriction first. And that's something new from these notes that didn't come up very much in our textbook. So spaces was one of the first strategies that we learned, and dealing with restrictions within that came up next. We've also learned about, well, I'm going to write it as a strategy just today, the not strategy. All minus the bad. Sometimes it's going to be easier to count the bad ones and subtract it from all of them than it will be to count things directly. We haven't come across a question where that's been the easiest way yet, because our odd number 1 was still easier to count using restrictions, but it's another strategy that we can use. We've also had identical objects. Those are our Mississippi questions. And what's going to happen is we are going to keep adding to this, getting more and more strategies, and then the questions you run into can use one or more of these strategies depending on how complex it gets. So that's where this unit will get complicated, is because every word problem is a little bit different. And sometimes you'll need to use one strategy, and sometimes you might need to use a combination of strategies to figure it out. All right, let's continue with factorial notation. evaluate each of those, simplify each of those without your calculator. Now, one of the techniques that we're going to use to simplify factorials, you can write 7, 6, 5, 4, 3, 2, 1 all the way down to 1 and 5, 4, 3, 2, 1 all the way down to the 1. If you really enjoy crossing things out, that's quite fun. But if these numbers were, say, 107 and 105, 107 all the way down to 1, and 105 all the way down to 1 could be quite tedious. So instead, what we're going to start doing is we're going to say, well, start expanding the bigger one, 7 times 6, and when you get to 5, just say, well, it would keep going, so I'm going to put an exclamation mark there because I have that same thing on the bottom, and all of those would cancel out. And the same thing, if you had 107, it would just be 107 times 106, and when you get to 105, write factorial to cancel out with the 1 on the bottom. This just leaves you with 42. Same thing on the next one. I would start 10, start with expanding the biggest one, and then when I get to 6, I'm going to stop because I know that that will cancel out with the 6 factorial on the bottom. Now with the 4 factorial on the bottom, that's 4 times 3 times 2 times 1. Can you see that 4 times 2 is 8, and that would cancel out? And the 9 and the 3, well, they wouldn't cancel out perfectly, but they would simplify, and you would be left with a 3 on the top. So I tried to color code things there so that you could see what I canceled with what. And now what am I left with on the top? A 10, a 3, and a 7. 3 times 7 is 21. 21 times 10 is 210. And finally, in the last one, with algebra, you expand the bigger one. So the first thing you have to decide what's bigger. N plus 2 is bigger. Expand 1 less than n plus 2 is n plus 1, till you get to n factorial. And those cancel out. See you guys, period 3.